Pop quiz. Which bond takes the most energy to split evenly into radicals? Think it through, lock in your answer, and we'll reveal it at the end of the video. In the next few minutes, you'll discover why some bonds snap with just a nudge, while others refuse to break. You'll master bond dissociation energy, the key to predicting which bonds are strong and which are not. You'll learn what bond dissociation energy, or BDE, means, how to read BDE tables, and how BDEs connect to reaction enthalpy and reactivity without memorizing a wall of numbers. Quick thermochem reset. When a reaction releases heat, it's exothermic. Its enthalpy change is negative. When it absorbs heat, it's endothermic. Its enthalpy change is positive. In both cases, bonds are broken and new ones are formed. BDE is the energy required to break one bond homolytically, so each atom keeps one electron, usually defined for the gas phase at a stated temperature. Every bond has its own bond dissociation energy, because factors like the atoms involved, their hybridization, and neighboring groups all influence bond strength. More S character usually means a shorter, stronger carbon-hydrogen bond. So SP is stronger than sp2, which is stronger than sp3. But not all single bonds are sturdy. The oxygen-oxygen bond and the fluorine-fluorine bond are surprisingly weak, thanks to lone pair repulsions. As a rule of thumb, shorter bonds are stronger. Also, more polar covalent bonds can be stronger. Compare hydrogen-fluorine versus hydrogen-iodine. But remember, BDE refers to homolytic cleavage. Polarity helps explain trends. It isn't the definition. For example, breaking a carbon-hydrogen bond in methane in the gas phase takes about 439 kilojoules per mole. That's the energy required to split it into a methyl radical and a hydrogen atom radical. You don't memorize BDEs. You use tables. They list average values for common bond types. Because values are averaged and conditions vary, treat them as estimates to compare possibilities or to rough estimate delta H. Let's estimate the reaction enthalpy using bond dissociation energies. First, we break the HH bond and the Cl-Cl bond. That's 436 plus 243 for a total of 679 kilojoules per mole in. Next, we form two HCl bonds. 2 times 431 gives 862 kilojoules per mole out. So, delta H is approximately 679 minus 862, which equals negative 183 kilojoules per mole. Negative means exothermic. We formed stronger bonds than we broke, so heat is released. So far, we've covered what BDE means, why atoms and bond length matter, and how to use BDEs to estimate reaction enthalpy. Ready to lock it in? Tap the link for study guides and flashcards on this topic, so you can keep learning without missing a beat. Now let's apply the idea to radicals. Allylic CH bonds break more easily because the allyl radical is resonance stabilized. Compare their bond dissociation energies, roughly 360 kilojoules per mole for an allylic CH, versus about 410 kilojoules per mole for a typical sp3CH. A lower BDE is often a clue to where radical reactions start. 3 gotchas. 1. BDE tables list averages, usually gas phase values. 2. Thermodynamics isn't kinetics. A bond can be weak yet slow to break without the right mechanism or conditions. 3. BDE is about homolysis, even split into radicals. Heterolysis makes ions and follows different energetics. Don't mix them up. Back to the quiz. Hydrogen chlorine HCl is stronger than hydrogen iodine, HI. But between hydrogen-hydrogen, H2, and hydrogen chlorine, Which is tougher? The answer is hydrogen-hydrogen, letter A. It has the highest homolytic bond dissociation energy of these choices. Hydrogen-chlorine is close, hydrogen-iodine is much weaker, and fluorine-fluorine is weakest because lone pairs repel. Quick recap. Bond dissociation energy, BDE, is the energy to break a bond homolytically, splitting it evenly into radicals. Shorter bonds tend to be stronger. Use tables to estimate reaction enthalpy. Delta H equals the sum of bond energies for bonds broken, minus the sum for bonds formed. Keep an eye on resonance stabilization and lone pair repulsion. They can shift the numbers. And remember, tables report averages. Usually gas phase and thermodynamics isn't kinetics. A weak bond can still break slowly without the right pathway or conditions. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.